Good morning, everyone. Welcome to our computational social science webinar in August. Today we are very happy to invite our colleague, Professor Zhu Lin from Department of Sociology. And also currently, Professor Zhu now is a co-director of the Computational Social Science Lab. Thank you, Professor Zhu. Let me briefly introduce Professor Zhu. Professor Zhu now is assistant professor of sociology. As I just mentioned, is also the co-director of the Computational Social Science Lab, and also associate director of the Center for Population Research Center at the Chinese University of Hong Kong. Hayes has very diverse interest, but basically using a lot of computational social science techniques. So as you can see later, the topic of today is to talking about the modularity score, which is about social network analysis. So without further ado, let's welcome Professor Zhu. Yeah, thank you.
Um,
Thank you.
okay. Thank you, Professor Liang, for your kind invitation and introduction. And good morning, everyone. Thank you very much for attending today's webinar. I'm very happy to share with you the recent work that I collaborate with Professor Liang Hai, as well as some other students and colleagues at the Chinese University of Hong Kong. As you can see from the screen, the title of my presentation today is Comparing Modularity Scores Across Different Social Networks Towards More Trustworthy Practices. So to give you some brief research background, as you can see from the title, the center word is modularity. So we will briefly introduce you for audience who are unfamiliar with the concept. I want to briefly introduce to you what is modularity and how it is applied in social science research. Specifically, modularity score is a quality function developed and introduced by two physicists, Professor Newman and Professor Gervin, in their 2004 groundbreaking paper. In this paper, they introduced this quality function modularity score, which they term as Q, so as to evaluate and detect the community and modular structure of a network. Specifically, this quality function has this characteristics, which is given a network, the higher the modularity scores for a certain community division, the more salient of that community or modular structure for that network, even though you do not know the network structure beforehand. So for example, in these three graphs, they represent three same networks, but with different community division. And the modularity score will be the highest when the community division is the optimal for the network. So with these characteristics, scholars can use this quality function to detect the so-called optimal community structure of a network by maximizing this quality function Q without any priori assumption about the number or size of subgroups. And the rationale is pretty straightforward and intuitive. And therefore, after its introduction and after its birth, many scholars in various disciplines have started to use this quality function in their own studies, and as well as social scientists. The early and most common application of modularity scores in social science is also to use it to detect the community structure of a social network. For example, Professor Gerber, in his 2011 AJS paper, he used the modularity to detect the relational classes of a network constructed by individuals' musical preferences so as to re-examine the cultural omnivoresis. But in the recent 2 decades, there has been a rising extended application. That is, social scientists started to compare the optimal modularity scores across different social networks so as to evaluate the variation of some network module-related substantive concepts. The rationale of this extended application is, since the optimal modularity score can capture or reflect the salience of a network's modular structure, and therefore the variation of the optimal modularity score across different networks should also be able to reflect the variation of the salience of the network module structures. And further, we can infer the variation of some module related features. So For example, this figure is adapted from Schwed and Biermann's 2010 as a PNAS paper. In this graph, you can see that there are three different networks, each with their respective optimal modularity community division. And the modularity score will be the highest when the network has the most clear-cut community division. So the rationale of this extended application is also straightforward and relatively intuitive. And after its introduction, comparing modularity scores across social networks has become prevalent in various social science disciplines and over a variety of research topics. For example, some scholars in science of science have tried to compare the optimal modularity of scientific citation networks over time so as to evaluate the evolution of the level of scientific consensus regarding some contestable research topics. Some political scientists and political communication scholars have tried to compare the optimal modularity of political networks over time and across regions so as to evaluate the evolution and variation of the level of political polarization or fragmentation in various cultural settings. And some sociologists recently have tried to compare the optimal modularity of job mobility networks over time so as to evaluate the evolution of the rigidity of occupation class boundaries. This literature is pretty vast, and we summarize the most representative studies in this table. This table is pretty big, so I'm not going into the details of this table, but to summarize some key information of this table. Theoretically, in this vast literature, scholars are interested in using modularity to capture three major substantive concepts by comparing modularity scores across networks. The first is the variation of the level of network polarization or fragmentation. And second is the variation of the level of consensus or common ground. And third is the variation of the rigidity of community boundaries across networks. And empirically, scholars have mostly used two major modularity measures. The most widely used and the dominant one is the Gervin-Newman function, which is the earliest introduced by Professor Gervin and Newman, which we term it as the GM modularity. It has the weighted and unweighted form, directed and undirected form. And recently, with the rise of the directed networks, scholars have also increasingly employed the lin-ram modularity function, which we call as the error modularity for these directed networks. But despite the existence of this vast literature and wide application of this extended application, interestingly, there has been few systematic discussion and robustness checks about the compatibility issues across for social scientists, even though some scholars in their studies have indeed given certain considerations in their empirical analysis by reweighting the network size or fixing the nodes so as to make the modularity scores more comparable across networks. But even though there are some strategies in this regard, there has been very few systematic discussions and robustness checks of the compatibility issues. So now comes our research objective of this study. Specifically, the primary objective of this study is to critically assess the common practice of comparing modularity scores across different social networks so as to draw conclusions about concepts like consensus, polarization, fragmentation, and boundary rigidity. But in order to achieve this primary objective and also to recommend strategies towards more trustworthy practices, we have the following four sub-objectives. First is to identify and summarize three major issues that can distort cross-network comparison. Second is try to illustrate the three major issues through toy examples and systematic simulations for audiences. And third, after illustrating the three major issues, we have tried to offer methodological guidance towards more trustworthy practices, such as recommending clearer construct matrix matching, separating community detection from measurement, network standardization, and triangulation with alternative indicators, etc. And last, we try to demonstrate the practical relevance of all these lessons by re-examining a published empirical study, China 2020 paper in AJS, that used modularity comparison to study labor market mobility rigidity and show how addressing network dependency issues can fundamentally change the research conclusions. So here we go. Before we provide our stake, first, why do we have this concern about the modularity comparability issues? Specifically, why are we concerned to what extent our modularity scores are comparable across different social networks? Let me recall, at its birth, when Professor Newman and Gervin introduced this quality function, their key purpose is that given a network, if modularity structure exists, we can use this quality function to search for the optimal modular or community structure within that network, right? And therefore, when these optimal modularity scores are compared across, rather than within the same network across different community divisions, but across different networks, various conceptual and empirical issues may arise. First, conceptually, those similar terms that are commonly measured by modularity scores to some extent are intrinsically highly different. For example, when we talk about community boundary rigidities, we emphasize mainly and heavily on the transitivity among communities for the network. But when we mention the level of polarization or segmentation of the network, we emphasize not only the transitivity among communities, but also the level of cohesiveness within each community. And when we mention the level of consensus of a network, which is the degree that a network has a common ground, then this feature depends not only the transitivity among and the cohesiveness within communities, but also the size of the largest community. So this leads to what we term as the concept dependency issue. It means that when we use the modularity score to refer to different substantive concepts, we can predict theoretically and hypothetically different or even opposite directions of modularity changes for the same variation of network patterns. This sounds really weird, right? So to help the audience to comprehend this concept dependency issue, we illustrated using the toy examples. For example, here, there are two networks, network A and network B, and in both networks, there are 6 nodes with 3 distinct communities. And the only difference is that for network A, the 3 communities are relatively equal to each other, but for network B, there is a dominant community with the largest amount of shared edges, 20, versus the other 2 communities, they only have 2 edges, shared edges. Now, given this network, let's consider 3 different substantive scenarios. In the first scenario, the 2 networks are the job mobility networks, in which the nodes are 6 different occupations. The edges here refer to the number of job mobility events among occupations in thousands, and the modularity scores here are used to capture the level of rigidity of boundaries of job mobility classes or communities. And network A is the mobility network in the year T, and network B is the mobility network in the next year, the year T+1. Under this scenario, assume that we have the same number of people in the labor market over time, then the fluidity of the overall labor market should have increased in network B in the year T+1 because there are more people started to change jobs. However, the rigidity of community boundaries of these 2 networks should stay the same because in both time period, there has been no cross-boundary event. Therefore, under this scenario, we will say that network A and network B have the same level of rigidity of community boundaries, and therefore we will predict same modularity over time. Now, clear your mind. Let's consider the second substantive scenario, in which the two networks are the audience duplication networks. And the nodes, this is the case in the field of political communication, contributed by Professor Liang Hai. So the nodes here refer to 6 different media outlets, and the edges refer to the number of shared audiences between these media outlets in thousands. The modularity scores are used to capture the level of audience fragmentation in the media field as indicated by shared media outlets. Network A is the audience duplication network in the year T, and network B is the audience duplication in the year T plus 1. Under this scenario, if we assume that we have the same number of audiences in the population over time, audience fragmentation should have increased from the year T to the year T plus 1 because of the stronger tie between media A and media B in the second time point. And this stronger tie indicates that the audiences in this period have a stronger tendency of self-selection, specifically in this community, and it becomes less likely to be integrated with the other communities compared to the situation in the first time point. So under the situation, we will predict that the network A will be less segmented and network B will be more segmented. Correspondingly, network A should have lower modularity while network B should have higher modularity theoretically. And now clear your mind. Let's consider the third scenario in which the modularity are used to capture the level of consensus of a network. Now in the third scenario, the same two networks, but the two networks now is the citation networks regarding some contestable scientific topics. The nodes here are 6 well-known research teams on that contestable topic, and the edges refer to the number of positive citations among these research teams. Modularity scores here are used to capture the level of scientific consensus for that contestable topic. And network A is the citation network in the year T with 6 published papers cited by these teams. And network B is the citation network in the year T plus 1 with 18 new back-to-back publications between team A and team B, so they mutually cite each other. Under this scenario, the scientific consensus about the contestable topic nonetheless should have increased from the year T to the year T plus 1 because the new breakthrough from team A and team B has been so substantial that it drives up the scientific consensus of the field. So with this reasoning, network A should have lower level of consensus and network B should have higher level of consensus. Correspondingly, we will theoretically hypothesize that network A will have higher modularity and network B will have lower modularity. Now let's put these 3 scenarios together. These are all the theoretical hypotheses. We can see that for the same variation of network patterns, when we are referring to different substantive concepts, we can predict different or even opposite directions of modularity changes. This is what we called as the network concept, as the concept dependency issue. It means that when we use modularity scores to refer to different substantive concepts, we can predict different or even opposite directions of modularity changes for the same variation of network patterns. And therefore, we have to choose the modularity score change, modularity matrix to match that concept carefully. And in addition to this concept dependency issue, empirically, there are also algorithm dependency issue and network dependency issue. For example, we have mentioned that there are 2 major modularity matrices. One is the GM modularity, and the second is the error modularity. For the same 2 networks, when we practically to calculate their weighted GM modularity and error modularity, we can see that while the GM modularity decreased from network A to network B, GM modularity stays the same from network A to network B. This means that different modularity matrix or algorithms can react to the same variation of network patterns in a systematically different way. So this is what we call as the modularity algorithm dependency issue. And in addition to the modularity algorithm dependency issue, there are also community detection algorithm dependency issue, which means that if we use different community detection algorithms to find the optimal community, the findings can react differently to the same variation of the modular structure and network attributes systematically. And in addition to the algorithm dependency issue, there are also network dependency issue, which means that some network characteristics that are irrelevant to the community or modular structure of networks, such as the number of nodes, number of edges, number of communities, and edge and node distribution across communities, can also impose systematic variations of modularity, even if the modular structure stays the same. In order to illustrate these empirical issues, including the algorithm dependency issues and network characteristics dependency issues, we have conducted more systematic simulations. Specifically, these more comprehensive and systematic simulations helps us to illustrate the algorithm and network dependency issues based on two extreme setups of predetermined modular structure, very clear-cut. The first setup is random graphs, which theoretically should have no modular structure. And the second setup is networks with disjoint communities, which theoretically should have the most clear-cut modular structure. With these two setups, these are some findings from the systematic simulations. But for the sake of time, I'm not going through the slides one by one, but want to summarize the key lessons from the systematic simulations. Specifically, if we consider an observed network, what we can observe as a weighted combination of graphs with disjoint communities, which means that there is indeed some underlying community structure in that network, and random graphs, which means some random noises like our regression data, then its modularity can vary systematically with network characteristics, including the number of nodes, number of edges, number of communities, and edge and node distribution across these communities, and the algorithms you use, including the random graphs generating algorithm, the null model you use, and community detection algorithm, and the modularity matrix you employed. Even if the salience of the modular structure is the same in the network's generating mechanism. So up to now, let me summarize the key issues, the three key issues in 2 dimensions of comparing modularity scores across social networks. Theoretically and conceptually, there is a concept dependency issue, and empirically and practically, there are algorithm dependency and network dependency issues. So considering the existence of these issues of comparing modularity scores across social networks, here comes our suggestions regarding the alleviation of modularity compatibility issues. Before we provide our recommendation, I think everyone will first ask, are there panaceas to address these issues? In other words, can we find some strategy that we can apply for all types of studies and scenarios? Unfortunately, the short answer is no, because the most network robust matrix may not be able to capture the interested substantive concepts. While the matrix align best with our substantive concepts would be more network or algorithm sensitive and require diverse strategies of adjustment. And therefore, rather than or instead of providing some panacea strategy to address this modularity compatibility issues, we propose a multi-step strategy towards more trustworthy practices. Specifically, here is the implementation framework of this multi-step strategy towards more trustworthy practices. First, we should always define our research question and the concepts of interest carefully. And then after we define our concepts of interest carefully, we can assess the conceptual alignment of our substantive concept we are interested in with the newly developed network robust modularity measures. Specifically here, I want to add that modularity compatibility issues, even though there is no systematic summarization of these compatibility issues in social science research, many complex network study scholars have already aware of these issues and proposed some strategies and some measures to address it. For example, some scholars have proposed a lot of network robust modularity measures, such as the modularity density or robustness modularity. But these measures have their own limitation for our social scientist application purposes. We'll go into it later. So after defining the research question, researchers should assess the conceptual alignment of their defined concept with the newly developed network robust modularity measures, such as modularity density, robustness modularity, etc. If there is strong alignment, then choose this measure, and the task will be simple. We can just conduct robustness checks on parameter selections. But if there is weak alignment, these network robust modularity measures cannot capture your interest concepts well, then possibly you should still turn back to proper conventional measures such as GM modularity or LR modularity. If you use these relatively network sensitive measures, then you will need to consider addressing the algorithm dependency issues and further to address the network dependency issues by applying size or density corrections. But whichever way you choose from these two sides, finally, we will recommend you to validate your findings with external and non-modularity based measures. And this is the implementation framework. We have also provided some more details for the alleviation of each of the three issues. The first issue is the conceptual mismatch issue, right? So there is no way out. This is the first and foremost important issue we have to address first. And for the adjustment to address this issue, the only strategy is to carefully choose modularity metrics whose variation with the network patterns can be best aligned with the predictions based on the logics of the focus concept. And we have also summarized the key characteristics of the three major types of modularity matrix, the GM modularity, LR modularity, which are more network sensitive, and the more network robust matrix, such as modularity density and robustness modularity. GM modularity, to some extent, is better to capture the level of scientific consensus in the network, but LR modularity will be better to capture the level of fragmentation, polarization, and community boundary rigidity in the network. And for the network robust modularity matrix, even though they are less sensitive to algorithms and networks you have chosen, but they can only capture the degree to which the clusters are involved in the network's generating mechanism. And regarding the alleviation of the network dependency issue, we propose first, as what a lot of scholars have done, to conduct robustness checks using different community detection algorithms to ensure the robustness of the finding. And also, we recommend to separate the community detection from the calculation of the optimal modularity, which is to detect the communities using non-modularity based community detection algorithms. We have also summarized some modularity-based community detection algorithms here, as well as some non-modularity-based community detection algorithms here. Regarding the alleviation of the network dependency issue, if you use the network robust modularity matrix, you don't need to worry about it. But if not, you are still using LR or GM modularity, which are more algorithm and network sensitive, we will recommend you to standardize the networks using bootstrap simulations rather than the conventional rescaling or reweighting strategies. We will go into details later. And also conduct robustness checks using non-modularity based matrix. Here we summarize some network robust modularity matrix and non-modularity based matrix, as well as some detailed steps of conducting the bootstrap simulations. So this is the suggestions and recommendations we have provided towards more trustworthy practices of comparing modularity scores across networks. Now it comes to the question, to what extent these lessons are really useful. To illustrate the practical preferences of these findings or these lessons, we have re-examined the rigidity of job mobility in the US labor market from 1989 to 2015 by replicating Chen and Pak's 2020 AJS paper. Specifically, in this paper, Chen and Pak's the author's objective is to use the network approach to detect mobility classes, job mobility classes, and try to compare the modularity scores over time so as to evaluate the variation of the rigidity of the US labor market. They have used the data of CPS ASEC from 1989 to 2015. Their networks are job mobility networks in which the nodes are occupations and the edges are mobility events between these occupations. They have used the InfoMat algorithm to detect the job mobility classes, and they have used the error modularity in the weighted and directed form so as to evaluate the rigidity of the boundaries of their detected job mobility classes. And this figure summarizes the key findings. The y-axis is the lin-ran modularity of the job mobility networks from 1989 to 2015. From this graph, you can see that the error modularity stays relatively constant before the late 2000s, but increased significantly afterwards. So their key findings and key conclusions is boundaries that constrain mobility opportunities have become increasingly rigid over time. But have the authors carefully considered the compatibility issues? Regarding the concept mismatch issue, they have carefully chosen the error modularity as their key modularity measures. As we have mentioned earlier, error modularity is relatively suitable compared to other modularity metrics to capture the level of fragmentation or community boundary rigidity across networks. And therefore, this is a relatively suitable choice to capture the community boundary rigidity as the author interested in. So this concept mismatch issue, to some extent, they have done a good job. And regarding the algorithm dependency issue, the authors have also carefully chosen to use the InfoMat algorithm in their key analysis to detect communities. An InfoMat algorithm is a non-modularity-based community detection algorithm, and therefore it can, to some extent, alleviate the compatibility issues as what we have suggested. And specifically, the authors have also done a series of robustness tests of their key findings using GM modularity and using modularity-based community detection algorithms, such as Louvain algorithm and fast-greedy community detection algorithms. And all these robustness tests confirm their findings. And therefore, regarding the algorithm dependency issues, the authors have also done a pretty good job. Now it comes to the network dependency issue. Specifically, are there significant variations of some basic network features across networks in the author's analysis analytical sample, such as the number of nodes, number of edges, and number of communities? This figure gives us this information. Specifically, regarding the variation of the number of nodes across networks from 1989 to 2015, we can get the information from the number of unique non-isolating occupations here. So from this figure, we can see the number of nodes actually decline steadily over time. And regarding the variation of number of edges, we can get this information from the number of between occupation transitions in this table. And this figure tells us that number of edges actually declined before the mid-2000s, but increased significantly afterwards, which align well with their modularity trend. And regarding the number of communities, also the authors have found that number of communities declined first and then increased after the late 2000s. So there are significant variation of some basic network features, which may not necessarily related to the modular structure or job mobility boundary rigidity level across networks, right? Then have the authors considered the network dependency issues? Regarding the variation of the number of nodes, there is no strategy to alleviate this issue. Regarding the variation of number of edges, the authors have assigned yearly weight so as to make them the same over time. And regarding the variation of number of communities, the authors have interpreted as showing the increase in segmentation of the job mobility level in the labor market. However, reweighting edges and interpreting the number of communities variation in this way is highly problematic, because reweighting edges in this way actually is a strategy to systematically adding or removing edge or edge weights that have no influence on the current network structure. For example, to illustrate the author's practice, what they have done is, for example, now we have this completely connected network with none edges. If I want to reweight it into a network with only 7 edges, the author's strategy is just to adjust the edge weight of each edge in this graph into 7 nines, from 1 to 7 nines, which to some extent is meaningless considering the formation of job mobility network, because it is impossible that a person just migrate from one occupation to another occupation with 7 nines chance or likelihood, etc. So this strategy is very problematic because it assumes that the community structure of a network is highly robust to adding or removing edges. But this assumption is too strong because, especially for networks that are relatively sparse, adding or removing edges can easily merge small communities or split large communities into subgroups. For example, in this completely connected graph with none edges, if I want to remove 2 edges, it can easily dissolve into a smaller network, but with 2 distinct communities rather than one comprehensive community. So we will disagree with this conventional reweighting strategy to adjust the network size. Rather, we will suggest that if we indeed want to alleviate the network dependency issue, we should first fix the nodes, and second, conduct the bootstrap simulations by randomly dropping the excessive mobility events, so as to equalize the number of edges over time and across networks, and do this for multiple times to check the robustness of the community structures over time. And this is our robustness check findings. The red line is our replication of the original finding. And the blue line and the green line is our robustness check findings. From this green line, we can see that actually we can successfully replicate their findings following their strategy. The linear modularity stays relatively stable before the late 2000s and then increased significantly afterwards. But after we address this network dependency issues, the shady areas is the 95% confidence interval of our bootstrap simulations finding. So after addressing this network dependency issue using the bootstrap simulation, we can see that even though we can still observe the rising trend after the mid-2000s, but the trend has become much wilder. Specifically, the uprise is mainly driven by the modularity rise in 2014, which nonetheless has very large bootstrap confidence interval. And if we remove this 2014 outlier, there's almost no trend after equalizing the number of movers over time. Now, last step, using external and non-modularity based measures, we can further check whether the labor market in the United States has become more rigid or more fluid since the late 2000s, using non-modulated based measure and even simpler measure, the immobility rate. This figure gives you the immobility rate from 1989 to 2015 across detailed occupations, micro classes, meso classes, macro classes, and the mobility classes as defined by the authors. And from this figure, we can see that if we look at the immobility rates across meso macro and mobility classes, they are actually constant rather than rising over time. And for detailed occupations and micro classes, the immobility rate has in fact decreased after the mid-2000s, which means that people are more likely to change their detailed occupations or micro classes after mid-2000s. This, nonetheless, seems to have suggested a more fluid rather than a more rigid labor market after the late 2000s. Okay, coming this long way, now comes to our conclusion. In this study, we have identified three major issues along two dimensions of comparing modularity scores across social networks: the conceptual misalignment issue and empirical pitfalls. There are algorithm dependency issue and network dependency issue. And to alleviate these issues, we have also provided guides towards more trustworthy practices. And to conclude, the key takeaway that I hope you can get from today's talk is that, to some extent, we are not saying that modularity is useless at all or problematic at all. We still think that modularity comparison across networks can be highly valuable, but we caution that it requires careful methodological safeguards so as to ensure valid measurement of intended social science constructs. Thank you very much. Now the paper is under R&R. We have received some suggestions from reviewers, but we also look forward to the comments and questions from the audience. Thank you.
Okay, thank you very much. Yeah, Eric. Yeah.
Well, first of all, thank you, Professor Zhu, for a wonderful presentation. I mean, I really am impressed with the clarity of the explanation, even though I'm not sure I understand it well, but I attribute that to my own failings as opposed to the presentation. I mean, given the overall thing that you're doing, I think it's a very valuable contribution, if indeed it has not been done already. And because I'm not familiar with this particular concept or how it's used, maybe others are already talking about concept dependency, algorithmic dependency, network dependency, etc. But I think that your nice explanation of how each of those might come into play is terrific, especially the conceptual dependency, right? I mean, so that seems very, very, very important, right? That depending upon what it is we're talking about, these things measure different things. That really means, I think, we've got to be careful. And so I think that, first of all, identifying the problem, and then, giving these very nice examples that illustrate the problem nicely, and then coming up with some constructive approaches and taking the paper, I forget the author's name that you took as your kind of
China
model.
Park, yeah.
Right. So I think the approach is wonderful. So, but um, but I think I'm struggling a bit just because this is the first I've seen of this concept. So I guess maybe one question that gets to the heart of my confusion, it may be that if I ask you've got these communities, right? You refer to communities, and then there are kind of edges between the communities, and you're looking at kind of flows between communities as a sense of their these kind of leakages, right? And lack of rigidity, right? If there are more flows between communities, then it's more fluid. If there aren't many flows, then it's more rigid. Is that the basic idea?
Oh, you mean the replicated study? For replicated study, yes.
I see.
But
So it's not a general thing. It was that specific application, right?
no, it is not that specific because the modularity measure is just used to capture the modular structure of a network. But
Well,
modular
yeah.
structure may not necessarily imply the substantive concept of fluidity or not. It may not.
Yeah. Okay.
Yes.
So actually, the fluidity is maybe taking us down the wrong path. So, well, I guess one question I have is, so you talk about communities. Are the communities exogenous to the study? So you talked about community A, community B, et cetera, right? Are
Mhm.
those are given, right? Because it seems to me that there may be endogeneity in the
Yeah.
communities themselves, depending upon what this thing means. And if in fact communities evolve on the basis of the interactions that you're observing, then that opens up a lot of potential for misinterpretation of statistics over time or likewise. So that's one question I have is just, are these communities exogenous?
No. The
They're
answer
endogenous.
is the answer is yes and no. It depends on how the scholars construct that community. So
Okay.
so if so for example, in our replicated study, um, if you can predefine it, like you can predefine it by using the microclass, because they are also type of community. If you group a set of occupations together, they are type of community, right? So if you define microclass, mesoclass, macroclass, they can be the community in predefined community in the network, in this job mobility network. However, it can also be endogenous. And most of the time, the communities in network studies are endogenous rather than exogenous.
They're
So they are,
inferred from the activity, in other words.
yeah, we scholars may infer the community structure from their activity, their move
Yes,
activity.
right.
And this is the problematic part. Yeah.
Well, that's kind of what I was, I guess, so that's where I was kind of hoping, my question about whether the communities are endogenous, exogenous, would lead. And so I'd like to ask kind of a prior question. The question I had in my mind before I got to that question was I guess I had imagined this in a different way when I read the abstract before I tuned into the lecture. And I was trying to think, well, what does all this mean, right? And what I was imagining, it's funny, you said 3 times when you're giving your example, you said, now empty your head or empty your brain, right? I was thinking, you don't need to tell me that. I came in with an empty brain. So I'm working on this. So what I had in my almost empty brain when I started, listening to this was I was imagining a network, right? That we had these nodes, that these nodes were individuals, and there were some kind of flows between nodes. That's what made it a network, right? They might have been individuals making telephone calls, they might have been journal articles referring to each other, all kinds of things, right? Any number of ways we can imagine that. And I had imagined that modularity was a way of just taking a given network structure with a given set of nodes and then assessing the extent to which the networks were somehow segmented from each other, almost like a cluster analysis, right? That that you would say, well, so imagine a kind of a street grid, for example. And we find that, well, in this particular geographic area, all of the activity seems to be between this intersection and that intersection, but everyone's kind of circulating within this sort of sub-network. And then next to that is this the same phenomenon in some other sub-network. And so that's the way we kind of infer these communities endogenously. We observe and say, well, look, these guys are all kind of circling around together in the same area. And so that must be some kind of network, right? And then, like what? And so I guess the initial question I came in with, in what way am I wrong in thinking that? That it,
I
you know,
yeah. I think I've received a scholar's question, a reviewer's question, because now the paper is under R&R, and we have received several fantastic reviewers' comments, and I think your question aligns with one of the reviewers' comments, which, if I understand it correctly, you are saying that what's the wrong if I come into a network, I have a network and I know the community structure and people are flowing across these communities, and then I use modularity to evaluate their flows intensity over time. So, for example, like this way. So what's the problem, right? Am I correct?
Well, you may be correct, but it's not what I was saying.
Yeah, but I think here there is one issue. It depends on, it goes to my previous comments. It depends on how you do the analysis. So if you come with a predefined network structure, you do not find, you are not trying to use modularity. So what's the common practice in the field is that people with a network, without knowing its true underlying network structure, and then they can only use the observed edges or flows or the network, the observed network to infer its underlying network structure. This is the common practice. Yeah.
So they're
it
seeing the communities and they're
yeah
seeing some kind of interaction between communities, but they're not
yeah
seeing so
they,
they're
they,
not
they have
seeing the
they have
network
no
structure within the communities.
they have no prescience of the network structure within those communities. No, there is no pre-knowledge of that.
Okay, well,
So
that does
people,
get back to my
yeah,
first question then, right? If they kind of
yeah,
stick with the
yeah.
concept of
So
community.
yeah, so here comes to my
Yeah,
further
yeah,
comments. If that
right.
was the, yes, people can still use modularity in that scenario, right? I come here with a network with predefined communities. Now I want to use modularity to evaluate the evolution of whatever concepts over time. But I have this network, and then I have this predefined structure. In that scenario, I would say that the compatibility issues would be smaller. Why? Because you are not using any algorithm to detect the underlying community of those networks, right? So if you are not using algorithm, then the algorithm dependency issue will be alleviated because it doesn't quite depend on any algorithms to find the
Right,
community first. And
right.
then, yeah, you already know the truth, the ground truth of the community structure, then it would be good. So the compatibility issue would be alleviated. But even under this scenario, you still need to address the network dependency issue, which means that you still need to address the network characteristics, because the network characteristics may also change over time, like the number of edges, etc. We still need to consider to an extent the change of those network characteristics. It's just like we are doing regression analysis across different samples. If we want
Yeah,
the regression results to be comparable, we have to do some adjustment of those
sure.
coefficients rather
Yeah,
than just to say they're comparable, because the
yeah,
samples is not the same. So it's the same here for the comparison of the same coefficient. Here is the network modularity. The same network modularity across networks, we need to make those networks comparable. And then, which means that we need to do some beforehand adjustment. And that's what we mean as the network dependency issue. We need to conduct
yeah.
some yeah. I hope I addressed your question, but this is a great question, and I do receive similar questions from the reviewers.
And good luck with the review, but yeah.
Oh, thank you, Eric. Thank you very much for the comments and questions.
Yes. Thank you for the question and also the answers. So any other question from the audience? Just
Am I very convincing? It seems that the presentation is pretty convincing, right?
yeah. That's perfect.
Yeah.
So any question for our own students? So you can feel free. Okay, Renee. So it's our new students from sociology. Yeah, go ahead, Renee.
Thank you.
Yeah.
First of all, Professor Shu, thank you. That was like I have so many questions, but like in particular, first of all, it was an amazing presentation. So it is really hard to make a question because everything is like crystal clear. But I guess that going more like to the specifics of when we are drawing the graph and these particular structures that that they arise from what we're observing, like based on your experience or based on this in these recommendations, like when should we assume that that's the structure per se of the graph, and when should we be like disturbing the like with the boost, not disturbing, but like resampling with bootstrap simulation? So in this case, you prove that taking by granted the structure might lead us to different results. But sometimes the structure might be just as it is, and we don't know like any counterfactual. Like I was thinking that maybe we could use this to make like kind of synthetic counterfactuals. I don't know if I'm being clear. Like my head is a mess right now.
Can you explain a little bit? So you are saying that
that part. Precisely that part.
Yeah.
So
precisely which part?
Next one. The
next one?
Yes.
This one? This one? This one?
Exactly. Yes. So for example, here what I understood, like if I understood right, is like we are taking like two nodes randomly and we do bootstrap sampling, right? But what
two edge, we are taking away two edges randomly and do the bootstrap.
But like what happens when when the edge removal is not randomly, like that when actually has like a specific like repeatedly pattern? I don't know if I'm like getting clear. So
okay. Yeah. Please I think my short answer is that if like Eric's question, you have pre-knowledge, you have prescience of the network structure, you do not need to worry of this step because you have already know the community structure and you can just draw it, right? But most of the time, because we do not have the pre-knowledge or prescience of the community structure, we have to infer it from our observed network. And if we want to equalize the network across if we want to make the networks with relatively comparable characteristics over time or across regions, across networks, we have to standardize like a lot of informations like the number of nodes, number of edges, etc. Specifically, number of edges. Existing scholars have tried to do that, and their strategy is just to reweigh the edges in from this to this, like this way. And here you are saying that if this pattern like I remove this the edges removal always similar two edges or similar edges have been dropped. Then if you do the bootstrap simulation multiple times and across multiple networks, the trend you can still identify, like here. You can see here, this is our bootstrap simulation. There is a still trend here. This is the mean distribution, right? But still, we can see that some networks, some period, their confidence interval is very narrow, which means that the network is pretty robust by adding or removing edges. But for some other period, after we remove the excessive edges, the network is not that robust. Even though we can see that the mean is still here, it's still like this way, but the confidence interval is very large. Bootstrap confidence interval is very large. I think you can still draw conclusion that we can still see the trend, but we should be careful for these peculiar years because they have very large confidence interval. And this is, I think, what you call as the alternatives or counterfactuals. So even though the network structure will be here, similar to this one, but we know that there are a series of counterfactuals distributing in this range. Okay. Have I answered your question?
Yes. I think I was just catching the wrong idea, but no, thank you. The clarification was really useful. Thank you very much.
Yeah, thank you very much, Renee.
Any other questions? So and you can back to the number 29.
Number 29?
Yes.
Finally, I got your comments.
So not comments because I'm not just some clarification on questions about this one. Yeah. So you mean the system reweighting? you mentioned the problem of the reweighting.
strategy. Yes,
Yeah, weighting strategy. The first thing you see that the reweighting is meaningless. Actually, I'm not. Why you think that it's
nonetheless.
meaningless?
Oh, I'm not saying no. I'm not saying the reweighting is meaningless. What I'm saying is that if we reweight it in this scenario for the job mobility network,
Mm-hmm.
because their number is not like it's not um their number is their in their original paper
Yes.
original paper the edge weights are actually integrals, so they are one,
Yes.
two, three, five. Yeah.
Yes.
So if we rating it in this way, there is
Mm-hmm.
actually strong assumption, which means that adding or removing edges should have completely no influence of the existing network structure. And
Yeah.
for example, if I just need to drop two edges so as to equalize the number of edge across networks, what their
Mm-hmm.
strategy is just to turn the edge weight of all the edges in graph one to make it into 7 nines in graph two, right? And if you think about in their original construction, their edge is actually integrals. This 7 nines is really weird
Mm-hmm.
because there is no like 7 nines people
Mm-hmm.
move from job A to job B.
But,
It
but
would be
I mean, you can reweight in another way, make all even in the reweighted network integers. You can do that, right? I mean, another way
can
to
you
reweight the network to
mhm,
ensure that all numbers are integers.
to ensure, but their strategy is
And
this one, and this is the conventional strategy.
what do you mean?
So So, so this is the reweighting that many people are doing. So if I want to reweight a network
Mm-hmm.
to stabilize to or standardize the network's edge, the total number of edge from network A to network B, like network A have 9 edges and network B have 7 edges, and I need to make network A's edge number is also 7. That my reweight is just in this way, right? But it means that but the unit of analysis is actually not in nines or tens. It's one. The unit of analysis is one. So
Mm-hmm.
I just need to follow the unit of analysis to remove or add edges, right? But here, the unit of analysis, if the unit of analysis is one, is an integral, is one, then you reweight in this way. It means that you are purposively reweighting the network so as to make the network structure stays the same, which also means that you have a strong assumption that the community structure is robust to adding or removing any edges in the network.
Mm-hmm.
And this assumption is pretty strong, especially for, yeah, maybe I have used a too strong word meaningless here. What I want to say is that it doesn't quite make sense under this scenario. It's not like meaningless. It doesn't quite make sense. But yeah, and it doesn't quite make sense because it has imposed a very strong assumption, which to some extent I think is not very realistic. Because especially for sparse networks, adding or removing edge or edge weights will highly um will influence the community structure in a pretty significant way.
Mm-hmm. Okay.
Have I addressed the question?
Yes.
Do you
So I
yes?
think that yeah, maybe I misunderstand the word meaningless here.
Yeah.
In
I
this
think it
context,
doesn't quite make sense. Sorry, I used too strong word here. I shouldn't say
yeah,
meaningless. I want to say is it doesn't quite make sense considering the substantive case.
yeah. So go to the 31, page 31,
31. Okay.
probably 31. Yeah, no, just 30. This one,
Mm.
for the comparisons. Um, I'm not sure the arrows. What are the? Is there are different colors, which means that
Oh, okay. There. So weighted and unweighted.
yeah,
So you
weighted
mean
and
the green?
weighted, but for the original AOR modularity,
Um.
there's no arrow.
There is no confidence interval.
Oh, they didn't provide the
They do, they,
confidence, and
yeah,
you
because
cannot calculate that, right? It just
they,
use the original
I think
ARM.
they can I think they can calculate it, but in their graph they do not quite provide it because they what they done is to use the Informat algorithm to detect the community, right? And then
Yes.
based on the detected community, they calculate error modularity. So if
Mm-hmm.
you use Informat algorithm multiple times, it is very likely that you will have achieve different modular community structure. So there should be a confidence interval here, but I don't, yeah, I don't think their confidence interval is large.
Yes, but this is my question actually. So you see the confidence in the error is very, very
Large
large.
here.
Yeah, I'm not sure
Oh,
why. Yeah.
it is because, oh, I can explain this. So their confidence interval will be narrow because they use the same network, right? Just
Yes.
use different algorithm. Just use the same network, same algorithm, same modularity measure. So the key variation comes from the algorithm. So if you use the algorithm multiple times, you may arrive at different network structure, and
Mm-hmm.
then community structure, and then based on different detected community structure, you will arrive at you will attempt different modularity scores, and you can map the modularity score distribution. But for the same network, if you apply the same algorithm, community detection algorithm, I think the variation will be pretty small because you will finally arrive maybe similar community structure. But here, our bootstrap confidence interval is removing to stabilize or standardize the number of edges over time by randomly removing excessive edges to
Mm-hmm.
make the number of edges to be the same as the lowest number of edge in these networks over time. So this large confidence interval exactly means that adding or removing these excessive edges can easily change the network structure. It is not like the algorithm, it is a network dependency issue.
Yes, I see, which means that if you see the change of the arrows over time, will also imply that actually the network structure that changed.
Yeah, so it means that for this several years, the network structure is not stable at all.
Yeah. So at least it means that they are very different from the networks in the early years.
Yeah, yeah. So that's exactly what we mean. And here you can see the uprise is mainly driven by the 2014 outlier. And after we remove that, there is obviously almost no trend of rising modularity. So the network dependency issue, as we have mentioned earlier, I think the authors have done a pretty good job in addressing the concept dependency issue and algorithm dependency issue. Now the key question or key issue here is the network dependency issue. They do not quite give enough consideration regarding the importance of the change of network characteristics to the change of modularity score. So the change of network characteristics, like the number of size, number of edges, number of nodes, number of edges, will significantly influence the network structure. And that will further influence their findings. And here you can see that even if we do not use the modularity measure, we just use the conventional non-modularity based measure like immobility rate, also based on their detected mobility class, so the endogenous class rather than exogenous one, it is also stable, right?
Mm-hmm.
And this means that the labor market, to some extent, at least, do not become more rigid. And this confirms our finding in this graph. It is pretty stable.
I don't get it. Why you saying the what I just observed is that the networks the network structure actually changed over time after 2002, right?
Yeah, yeah.
Yeah, but you see that it's stable.
No, I'm not saying the network structure. I'm saying the
Mm-hmm.
rigidity. The
So the
rigidity.
rigidity is stable, but the
Yeah,
network structure changed.
the network structure, I would say it become more, yeah, yeah.
So this is interesting. This is another again. This is another your problem in the current context. I mean, probably in the future study, if there is a really you see that from the picture here, there must be some very substantial, significant changes in
Yeah,
network structure, but we don't know what's that, right?
yeah, that so
And
you
initially,
you
it's
know
not the rigidity.
you know what, that's exactly why I think revising this part is to some extent is hard, because the reviewers, one of the reviewers' comment is exactly whether we have two papers or one paper in this study. Because to some extent, the second paper, this part, can stand alone, because our finding to some extent challenges the finding of a widely cited and top tier journal publication in AJS in 2020, and also widely cited paper. But our finding, our robustness checks found that the results is not quite the same. And one of the reviewers exactly here, because in our paper, to some extent, we do not want to quite dig into the substantive discussion, because we want to emphasize this is still a methodological paper, but we just find that after addressing the network dependency issues, actually the trend does not rise. And we just want to use this as a case. But one of the reviewers feels that there is something interesting. We need to elaborate on this part to give more substantive interpretation regarding like why we observe this trend and provide more explanation. So yes, we are struggling to an extent we can do this, because that if we give more substantive explanation emphasis on this part, it becomes less methodological for this paper. But
Yeah, I
yeah,
mean, actually, you can do a second paper, so
no,
to really to focus on what actually changed over time.
yeah,
The
yeah,
yeah, the market structure had it's clearly that it's something changed, but it's not a rigidity, but it's something else.
mm-hmm,
Can you guess
yeah.
what's that?
Oh, I think I can guess what. So, the key issue is that the rising trend is not driven by the change of community structure, but driven by the rising number of mobility events within the community. So there has been more people changing jobs within the community in several time points. There have been more people changing. So if we remove this excessive job change events within those communities,
Yeah.
underlying communities, then if we do it multiple times, because those excessive numbers is so large that if we move randomly drop this number,
Mm-hmm.
it will change the community structure significantly for the same network. So in different ways. And that's why for this several period, I guess it is because when we see the rise or stable, it is because the community the number of job mobility events comes more from within community
Okay.
job
Yeah.
mobility events rather than cross community job mobility events. And so when we want to remove those excessive job mobility events, it will influence the community structure, the detected community structure significantly. So I guess that may be the reason. That is also comparable to this one. So there has been a decline of immobility rate. So if we look at the detailed occupations immobility rate, so here immobility rate means people stay in the same occupation or same microclass or same mesoclass. The percentage of people staying the same detailed occupation, microclass, mesoclass over time. So here you can see the immobility rate actually decline here, right? What does it mean decline? It means that more and more people actually change their detailed occupations or microclasses within the same mesoclass or macroclass or mobility class, because this immobility rate stays constant, but this decline. So it means that more people trying to change jobs in the community.
Mm.
Yeah. But that doesn't quite mean the boundary become more rigid. It just means that the labor market become more fluid, but the fluidity started from the same community.
Okay, thank you very much. Is there any questions? Are there any questions from the audience? If no, so we stop here, and thank you, Professor Zhu again. So yes, so we see you next month for our CSS webinar in September. But today, thank you again, Professor Zhu.
Yeah. Thank you for everyone's attendance. Bye.
Yeah, bye.